Hello there and welcome back. We are covering chapter 4 today. Chapter 4 is on planar centers of gravity. Planar centers of gravity. First, moments and volumes of integration. The last set of lectures covered equilibrium in 2 dimensions, equilibrium in 3 dimensions. Then we moved to the definition of the moment of a force. So we did some vector algebra and we looked at the scalar and the dot product. Then we calculated some moments of a force at a point, about a point. And then we calculated moments of a force about an axis. Thereafter, we learned about equivalent and equipolant systems of forces. So we're basically converting a system of forces that are acting on a rigid body, and we converted a plethora of forces into just one resultant force at a chosen point of ours. We don't have to put it at the origin, any point. So there's some conversion steps that we learned there. Then after converting to some resultant force at a particular point and the moment resultant, we noticed that you can actually decouple that resultant force and its moment resultant into what we call a range. So a range would mean that you get a scalar product of that moment resultant onto the resultant axis. Then you would have another axis, so that if you move your range to another convenient point, you actually eliminate the lateral moment vector. So now that we know that we can find a resultant, right, after a number of forces, then it means we can now attempt to find a center of gravity, because any rigid body is made up of small particles. Those small particles have a weight. Each and every particle has its own contribution of a weight. Then all those weights are then added up to make the resultant, which we call the weight of an object. So we'll also learn about centroids and how we can locate a certain point geometrically at which, if the material is homogeneous, its weight will act. Right, so let's jump right into it. So the first section is on planar centers of gravity and centroids. Planar centers of gravity and centroids. There are 4 principles that we will take a look at in this section. Right, the 4 principles that we will take a look at are as follows. We are looking at the center of gravity of a 2-dimensional body, right? We will also learn about centroids, of areas and lines. Then we will move to first moments of areas and lines, and then composite plates and wires. Right, centers of gravity, or center of gravity of a 2-dimensional body. When we are talking about a 2-dimensional body, we're just looking at a plane, right? That's why in our diagrams here, you will notice that we are just dealing with some body that is in the XY plane. Now, the center of gravity is a point at which the resultant of all the weights acts. So it is a location, it's a geometrical location. Now, in this case, we explain, or we get a picture of the center of gravity from these 3 diagrams. Remember, a rigid body is a body, or it's an object that is made of small particles. So those static particles, we also did some statics of particles, excuse me. So this body is made of those particles. So in this diagram, figure A is showing some body which is aligned, or it is placed on the XY axis. So it is a plate in 2 dimensions of some thickness, which we can also as we can approximate it to be equal to 0. So any particle on this object is located at its y location. Remember, we're looking at 2D. So its small weight of that particle is given by delta weight 1. If we have multiple elements of the plate, then we will have a number of particles. So for example, our first particle, which was located at x1, y1, will also be added to some other weight of a small particle, weight 2, at x2, y2, and so forth until we get to the nth particle. When we have found the set of particles, this arrangement, this conversion from these separate particles that make up a rigid body to just one weight at a particular center of gravity is exactly what we were doing with the previous conversion. Still remember the example of the children that were on a raft, right? So they have different weights, and we were supposed to find the resultant weight and the point of action of that weight. So you were to look for instance, the moments about the x-axis, the moments about the x-axis. For that one, it also had the z-axis, right? Moments about the x-axis. Then same applies if it were this one, would say moments about the y-axis, moments about the y-axis, moments about the y-axis. So when you have found all those moments, obviously the resultant weight is just a sum of all those. When you found all those moments, you can then make use of the equation for the moments. So I think you still remember this equation. The equation for you to find the moment, for instance, about the y-axis. It is simply given by the distance about a perpendicular distance from the y-axis, which will be your x bar, right? So perpendicular distance from the y-axis, which will be your x bar, multiplied by the weight. Then this is the weight of the what? Of the resultant. We said from last time, this is equal to a sum of all the individual moments of the particles that make up the rigid body. This is why we have x bar weight is equal to x1 weight 1 plus x2 weight 2 and so forth. So in other words, you just have some distance multiplied by the weight is equal to the sum of the distance of each of the individual particles multiplied by its own weight for particles 1 up to n, or maybe small letter n, according to this convention. So the same applies for moments about the x-axis. You would need a y distance perpendicular to that axis, which is multiplied by the resultant weight, which is equal to the sum of all, which is this equation. Okay, so now this calculation actually gives us the center of gravity, because if we find the resultant and its location, that is the point at which the force of gravity has its weighted average point of application. That's where it is applied. So therefore that location is actually called the what? The center of gravity, or CoG, from the acronyms that I'm just creating here. Right, so that's the center of what? Of gravity. So if you want to find the x bar, it's obvious that from, let's say, equation star, you would just divide everything by W. So this is what we have on this part. So the equivalent and equivalent systems, should I say theory, is actually useful here, and we can get to see how it is applied. So that is why equation 5.1 is the equation for one to calculate the center of gravity. Now, if we have a case where those particles are made tinier and tinier, remember, we would want a case where we can just divide this. Let's say if it's homogeneous, right? We can just divide this body and we have particles that are of the same size. But it would never happen because this body has its own what? Curvature. So if you look at, for example, that particle, let me actually use another color. So this particle and the particle at the boundary, they wouldn't be the same. So which means our summation process fails when we approach reality. For this reason, we can actually then use calculus methods, because we know with calculus we can approach the limit where the delta weight is almost equal to 0. So at that limit, the total weight is simply now an integral of the infinitesimal weights. Then this means that our x bar weight equation, this one, is now equal to an integral. So instead of it being a summation, it's now equal to an integral with respect to the weight. The same applies for the centroid. So for the moment about the x-axis, which is y bar weight, it's equal to the integral of y with respect to the weight. It means, therefore, you can now summarize and find the centroid by using an integration equation. Now these concepts are now extended. That's the beauty of engineering. The beauty of engineering is we look at the physics, right? We argue a case and prove at a particular case. Now that the proof is there, we can now extend the same concept, because this body is just the same as having a very small portion of that body sliced out of it to make a wire. So it will be exactly the same for us to find the centroid of a wire that is in a plane. So this wire, remember, it's in a what? It's in a plane. In other words, you squash the wire until it is now flat. So whatever geometry it has, it should be flat. It should not be in 3 dimensions. I think you get the point. So you can now have a single element and use the same methods of analysis. At a particular point, we've got some weight W1 at x1, y1. Then you can have several weights that are what? That make up the wire. For you to find the center of gravity, you apply the same principles so that you come up with your resultant weight at some particular point. And we are not really now using those conversion methods. This part is assuming that that has already been done, because you already have the tools. So we are already supplied with the with some values which you can calculate with. So you've got your weight there, and then the center of gravity is that point x bar, y bar, which is found from these equations. So basically that summarizes the center of gravity of a body, the center of gravity of a 2D body. So in this example, we have an application of our case. So we have some body, right? We have some body, and if we were to use the x-y axis, if we were to use the x-y axis to describe its individual points or individual particles, this body has a, let's call it particle 1. So it will have it. Okay, so these are forces. Let me just put them as a weight, right? So it has a weight 1, delta weight 1 at that location, and that location is what? -2 minus 1, -2 minus 1. So basically that is what the x1 y1 means. Then we have another particle at some location there, and this particle, let's call it delta weight 2. It's at its own what? x2 y2, which is a 0, 4. We have another particle there. It is a delta weight 3, and it is at a point 1, 2. We have another particle here. Is it? No. It's supposed to be somewhere here. And this is maybe delta weight 4, and it is located at 6 minus 3. 6 minus 3. So that's our free body diagram. We've got some particles at which some weight is acting. So the question says, find the coordinates of the center of gravity of particles of weights 4, 7, 3, and 6 newtons at the points 1, 2, minus 1, minus 2, minus 1, 6, minus 3, and 0, 4 respectively. Right, so for us to find the center of gravity, which is equal to what? X bar and y bar. X bar, y bar. For us to find that center of gravity, we can apply our equations, right? So using the equation that states moment, for example, moments about the x-axis, we will get a y bar multiplied by the total weight, and this is equal to y1 for delta weight 1 plus y2 times delta weight 2 plus y3 times delta weight 3 plus y4 times delta weight 4. So this implies then that your y bar is, what is y1? So we're looking at the first particle. Y1 is a minus 1. What is delta weight 1? Then you write its value, so it's already given for you. What is y2? Y2 is its position is a 4, and this 4 multiplies a delta weight 2. What is y3? Y3 is at position 2, so that is a 2. It multiplies a delta weight 3, and then plus the last one is y4. It is at minus 3 multiplied by a delta weight 4. So you also do some thinking, right? Remember, we will divide everything by the sum of the delta weights from I equals to 1 up to 4. So remember, look at your moments. These are moments about the y-axis. This weight, weight 1, it is obviously non-zero. So about the y-axis, it would generate a what? A moment that rotates in such a way that if we look at it from the y-axis, remember these weights are into the page. So if we look at it from the y-axis, it actually generates a what? A positive moment, because it is anti-clockwise, right? Then if you look at the 6 Newton force, which is right here, right? Our 6 Newton force is right on the y-axis, so it has a 0 moment about the what? About the y-axis. Then if you look at the 4 Newton force, it would have a what? It would have a negative moment about the y-axis. Yes, negative moment, because if you look at it, it would generate a what? Sorry. If I look at it from up there, what will I see? I will see rotation. Right, so I'm looking at it there. Yes, it will actually be a positive moment. Yes, it will be a positive moment. This one is what generated a negative moment. And then this one will also do the same. When you look at it from up there, it will generate a positive moment. The same applies with our the moments about the x-axis. Our first particle about the x-axis is below the x-axis. If we look at it from the x-axis, it will generate a what? A clockwise moment. And then when we look at this particle at that point, so which means basically what we're saying here is when you get the distances and the weights, you also need to be careful as far as the directions of the moments are concerned, because when we look at moments about the x-axis, we are looking at the arrangement from the x-axis, and we look at these forces. This force is actually in the if we were to look at the force, it's actually in the negative k direction. Yes, it's in the negative k direction. So which means if it's in the negative k direction, then from the math you should be able to figure out the directions. So just be careful of that. Just make sure when you've written your equation, it actually makes sense to you that, okay, I'm rotating about the x-axis. My 7 Newton force is on the negative side of the x-axis. If it is into the page, this means, by the way, these forces, we were not told if they are into or out of the page. So we're just assuming that it's into the page because they are weights. So if it's a weight into the page, what moment is it supposed to generate? It's supposed to generate a positive moment. Okay, so that covers an example on the center of gravity of a 2D body. The most important thing, don't forget that these positions are actually positions. on an x, y, or maybe z axis. And if it is in the negative sense, put that position where it's negative, so it's a negative 1. Right, so that covers the first principle on centers of gravity. The second principle on centroids and areas of areas and lines. So what is a centroid? A centroid is a geometrical location, right? A centroid is a geometrical location, x, y, if it's in 3D, z point. So it is a geometrical location which defines the geometrical center of this object. If it were a square, the centroid is exactly half the length, half the height. If it were a rectangle, it's exactly half the length, half the width. Now, for us to find centroids now, the idea is there are some materials that are homogeneous, like we said. If they're homogeneous, then these materials have an even distribution of the particles and their weight. So we can actually calculate the centroid of that material just using the geometry. We don't even need to consider the weight. So how do we do that? The equations here, they rely on the definition of a new variable which we call the specific weight, given by this Greek letter. I think this is a gamma, right? So it's given by the Greek letter, it's a gamma. If it's not gamma, please pardon me. You may look for its correct name. So if we have this letter, let's look at its meaning. The specific weight is the ratio of the weight to the volume of an object. The specific weight is the ratio of the weight to the volume of an object. We know that in the SI system of units, our weight is simply mg, and the volume is given by V. And we know that our rho, which is the density of the material, is equal to mass over volume. So this implies this equation. It implies that the specific weight of an object is given by rho g. Now, so I'll just do that. So when we have an object with some weight, we can express its weight in terms of the specific weight, because the specific weight is just a weight per unit volume. It will not change, right? So the specific weight is a ratio that we can use. This means that for us to get the weight, for us to get a small weight, we would need that weight per unit volume multiplied by the volume of the object. That weight per unit volume multiplied by the volume of the object. So if we have our weight per unit volume and the volume of the object is given by its cross-sectional, its thickness multiplied by its cross-sectional area. This implies that we can replace this and we get a gamma multiplied by T multiplied by delta A. This is the source of this equation. So basically what we have done in this equation, we have defined the weight in terms of the specific weight, the thickness, and the cross-sectional area. So for objects which we are summarizing to be very thin, right, objects in 2 dimensions, we can actually assume this to be a constant that we can assume to be 1, and it doesn't affect the equation. If for a small particle that is the case, then for a total of the particles, the case is the same. Our weight is now equal to the specific weight times the thickness times the total area of that material. Now this total area is what we're trying to use, because we know that we can actually do away with the constants. How can we do away with those constants? Why are we trying to do away with the constants? Because we want to come up with the equation for the centroid of an area. When we have an area, we deal with geometries. We don't even worry if the material is homogeneous, then we don't worry about its density and so forth. Right, so when we have this equation, we can plug this equation into the previous equations, right? So the previous equations defined the moment about some axis, let's say moment about the y-axis, as that equation, right? So we can now substitute what we have in the previous equation. So our x bar is now multiplying the total weight. The total weight from our previous equation has got a gamma multiplied by T multiplied by the total area, right? Gamma multiplied by T multiplied by the total area. This is equal to, now we're looking at this right hand side. So let me just use the summation, right? So this is a summation of our xi, and our delta weight is now equal to what? Is now equal to that gamma multiplied by the T multiplied by the delta area I, right? And our I is equal to 1 up to n particles. On the right hand side, you will notice that we can actually factor out our gamma T because these are constants. Then we can leave the summation sign within xi delta area I, right? On the left hand side, we said we can also factor out our gamma T, and we have the x bar multiplied by the area. So this gamma T, as you can see, it is what common on both sides. This is what generates this equation for the centroid of an area. So this equation is what is summarized by the steps that we showed just now. So it means for you to find the centroid of an area, all you need is the geometry of the object. All you need is the geometry of the object. The moments about the y-axis give us an x bar A, where we had W, we now have what? We now have area. And this was once W is now replaced by area, and we know that is because the weight per unit volume product with the thickness of the object are common on both sides, and these are constant. So we now have this equation which we derived just now. So by the same order of principles like what we had before, if we are now dealing with realistic particles, right, for the ideal case, this is the process of coming up with the summation, where you divide this whole area into neat and regularly shaped and equally shaped delta areas, right? But we know that in reality our objects will not necessarily give us a delta area. We would need to make, for us to make this particle excuse me, the same as this particle that is close to the boundary, we just need to reduce these particles, right? That's why we will end up transferring this to what? To dA. So that process of changing to dA is what gives us the integral case, or the integral equations. So once again, our particles of an area are divided into elements, and which means each area element is located at some x, y coordinates. Now, if we have each area element at some x, y coordinates, this means by the same method as we discussed earlier, we can find the centroid located at what? At x bar, y bar. We can find the centroid located at x bar, y bar, the same way we found the center of gravity. So the integral case is where our x bar is now given by the integral of x with respect to the area divided by a, the integral with respect to y divided by a. Right, so that is what generates our equations for the center of gravity. So by the same sign, by the same method, we can transfer this to a line, right? I think we had some equations for the line in the previous case. So if we have a line, it can be divided into what? Into different sections, and those different sections are now the what? Are now the elements dl. These are now the elements dl. So when it is regular, we can put dl, but if we want to be realistic, this dl must approach 0, so it becomes a what? A dl in terms of small letter d. So that element, that length element, is located at what? At an xy position. And if it's located at an xy position, then we can find many elements at their individual xy positions until we find the centroid at x bar, y bar, using the same method and equations. For this reason, we also have these equations that define the centroid of a line object or a linear object. And this is plane linear, right? Remember, this is a line, even if it wiggles, right? But it wiggles on the same plane. It's like a line that you draw on your piece of paper. It's on the same plane. It is not going to wiggle and then go under a plane. This is where we still are, the simpler case. Right, so to make use of those ideas, we can find the centroids of areas and lines using question 5.1. Question 5.1 requires you to locate the centroid of the plane area shown. This is the plane area that you have here. If you were to just sketch it here, it is actually a full rectangle minus a triangle. So you can think about it in many ways. You can think about it in many ways. You can think about it as a full rectangle, or minus a triangle, or a rectangle plus a triangle. So let's just do rectangle plus a triangle and call this area 1, call this area 2, and then this is our origin O. So this is where we have material, right? For us to locate the centroid, right? By the way, back in the day, I don't remember seeing a textbook from recently using this, but back in the day we would write the centroid with that sign. So it would be centroid is equal to that x bar, y bar. Okay, but no big deal. So on this side we have some height, let's call that h. On this side we have two lengths, so let's call this L1, then we have L2, right? So it means then for us to find the centroid, we need, the centroid, we need to use the equations for the x bar, y bar. So those equations simply stated that if we were to look at moments about the y-axis, this would give us x bar times the area, which is equal to x1, let's just say summation, right? So let's just say summation of xi delta ai from I is equal to 1. In our case, we've got two elements, so I up to 2. Now, let's expand. What is the x centroidal position for the first area element? The first area element is a triangle. So you can, I think by now, you should already know that the centroid is what? Is 1/3, isn't it? 1/3 of the height. So if it's 1/3 of the height and we're looking at our centroid on the x-axis, this is the, let me call this h bar. This is the height that we're looking at. If it is 1/3 of the height, it is 1/3 from this particular line that divides areas L1 and L2. This means from the reference point 0, our centroid is actually, excuse me, located at 2/3 of the height. So I'll call that L1. Multiplied by the area of a triangle, that's obviously half base times height. So you can choose any of these to be the base. Let me choose the L1 to be the base, and then the height to be h, half of the base L1 times height. Then the second particle is our, is it a square now? Yes, it's a square. It's a 45 by 45 now. So it's a square. So that's obviously this position. Remember, we're looking at position and not just 45 divided by 2. We're looking at position. So we should start from what? From L1, right? So this is our x2. So that's an L1 plus half of what? Of L2. Plus half of L2. That is the x bar multiplied by that area. That area is a square, so it's side squared, so we'll just call it what? L2 squared. So we have now found the right hand side of the equation. All these are numbers, so you can just use all these numbers. And your total area, obviously on your left hand side, you would now have our x bar would now become what? So the first one would be 1/3 L1 squared times h. This must, we should add L2 squared into L1 plus half of L2. This is now divided by the total area. So the total area is A1 plus A2. So what is that? That is our half AB, half base times height, which is this one, half L1H plus the L2 squared. So you now have your X bar. By the same method, you can then find your Y bar to find your centroid. So that is by the use of the equations that we got earlier. If you would like, you can also use the rectangle as it is and just subtract this, because when there is no material, it means we can actually subtract, because what are we doing? We are summing up the moments due to the areas. So these areas would produce so about the y-axis, if we were to look at them as areas which are into the page, about the y-axis, these areas would produce a anti-clockwise moment about the y-axis, right? Anti-clockwise moment about the y-axis, that would be a positive moment. This should now be an area in the opposite direction, so it should produce a negative moment. So it would be, if you look at it, it would be clockwise. Yes. Okay, fine. So I think we've got several techniques of attacking these questions. Now, if you want to tackle the third concept, you're looking at the definition of something called a first moment. So first moments of areas and lines. By definition, a first moment is defined using the symbol Q, and this first moment is simply equal to the calculated integral of x dA. So that integral, if you remember, it is actually that moment of an area which we calculated earlier. Look at that equation. Look at this equation. It's exactly the same, right? So in other words, your first moment about the y is actually x bar a, which is the same as the integral of x with respect to the area dA. So that is the definition of the of the first moment. The first moment is trying to capture this idea. We said we learned about the center of gravity. That's fine. We know that the center of gravity is found by looking at the moments of the resultant and the moments of the individual particles. That's fine. Then we discovered that, oh, okay, we don't really need to use these weights. We can actually eliminate the specific gravity thickness product and remain with moments in terms of areas. Moments are conceptually the same, right? The moment that you're calculating with the forces is the same moment that you're calculating with the areas. The only difference is that you found a way of mathematically eliminating certain parts of the equation until all you have, or all that remains, are areas. So if we have areas only, a first moment is the moment of an area, if you would like to summarize it that way. A first moment is the moment of an area. A moment that we learned earlier was the moment of a force. A first moment, you're just looking at it as the moment of of an area. And the good part with the areas is that areas are either positive or negative. It's either there is material that's into the page, there's no material that's out of the page, or the reverse, whichever convention you define. So the first moment is basically a moment of an area. This is the same as our, for this one, it will be y bar a. Right, so this is what this equation is telling us. It's simply equal to y bar a, so x bar a or y bar a. So you can actually use the first moment equation to either find the centroid or to find the integral part of the centroids. Now, there is something interesting with objects. There is something interesting with objects. If we are dealing with regularly shaped objects, regular shapes like a square, for example, or a rectangle and so forth, these objects have some special property which is called symmetry. So if you look at this figure, for example, the line BB prime is a line that describes what we can call symmetry. It's a line of symmetry. In other words, if we would fold this object about the line BB prime, we would not be able to tell which side we are looking at if we were to hold the object, let's say from afar, right? If you fold it neatly about that line BB prime, you can't, it's symmetric. The side on P will look the same as the side on P prime. So if you were to define this P prime as, for example, your x-axis, your moments about the y-axis, which is the BB prime axis, sorry, it's y. The moments about the y-axis would constitute of some area, remember we're looking at the first moments, multiplied by its what? Its perpendicular distance from the y-axis, which would be this, let's say, x bar position. So if you're looking at the moments on the right hand side, they, remember we said for areas we can assign plus for into the page or minus and stay that way. So this side P prime would generate a moment that is anti-clockwise about the y-axis, right? I'll be trying to think on the directions. So if I had to look at it from the y-axis and you look at this moment that is into the page, it would generate a what? An anti-clockwise, that's a positive moment. Then if you look at the moments on this side, which is the minus x, that would be then the what? The positive moment, which is a minus about the y-axis. So because of that, you would notice that your sum of the moments about a line of symmetry, they would actually add up to 0. They would actually add up to 0. For this reason, lines of symmetry are useful, because we now know that if the moments about the BB prime axis are equal to 0, then our centroid must be located somewhere here. Our centroid must be located along that line of symmetry. The same applies with this object, 5.5b, where we have some moments due to the area element dA and moments due to area element dA prime. These are at a distance x, these are at a distance minus x, so they add up to 0. This means that our this means that our centroid is actually located at a what? At the position x is equal to 0. Our x bar is actually equal to 0. So whenever there's symmetry, this slide is just telling us that we can take advantage of symmetry so that we don't have to think that much. All we do is, we've seen that there's symmetry. If there is a line of symmetry, then our centroid must be located on that line. All we are doing is to now calculate our y bar using the first moment about the x-axis. Right, so this implies that you now have some ideas which you can make use of to find the first moments for objects that have symmetry. So if an object now has two lines of symmetry, then this slide is just extending the idea and telling you that that object will have its centroid at the intersection. It actually makes sense. So same applies for figure 5.6b. However, there are some situations where you can have points of symmetry, but not a line of symmetry. When you say points of symmetry, it's the same as this. This is a point of symmetry. This is a point of symmetry. If you were to fold this object along this axis, you can't see the difference between P and P prime, right, at that location. If you are to look at these points are symmetrically, they are equidistant from the origin, right? But they are not. This does not form a line of symmetry. They're just points that are symmetrically separated from each other. So an area may actually have a center of symmetry, but no axis of symmetry. So just be careful with your geometries so that you don't quickly assume that we've got some symmetry. Right, so making use of symmetry, there's an example on first moments of areas. Question 5.22 is saying the horizontal x-axis is drawn through the centroid C of the area shown, and it divides the area into two component areas A1 and A2. Determine the first moment of each component area with respect to the x-axis and explain the results that you obtained. Right, so we have this object, it's about the x-axis. So if we draw it like that, this object has symmetry by inspection. If you look at it, you can tell if this distance, let's call it D1, right? For the sake of space, or maybe let me just try, but for the sake of space, I think let me just annotate the actual diagram, right? let's see. Okay, this is not going to work. So let me just annotate the actual diagram. In your writing, you may need to annotate your own diagram. These distances, let's call this x1. X1 is exactly the same, right, from there to there. So it's obvious here we have what? We have, let's say, x2 and x2. So it's obvious that here we would have the same distance. So if we were to call this, this is A and C, let me call this B, and then maybe B1 and B2. Yeah, something like this. So by inspection, you can tell that, no, this object has the same, it has a line of symmetry. The y-axis of this object is a line of symmetry. Its centroid must actually be located on that axis. This is why they're asking us to find the first moment of each component area with respect to the x-axis. Because with respect to the y-axis, the first moments should add up to 0. So with respect to the x-axis, the first moments about the x-axis would be a y bar A, which is equal to what? The summation of y I delta A I, and this is from 1 up to 2. This is from 1 up to 2. Now, when you look at this section is exciting because you're already given some tables, right? There's some tables. If you look at your reference tables, you can actually find the first moments of these regular shapes. Okay, so if you want to find this first moment, this implies that since this is difficult, this y bar A, we can't by inspection just say our y bar is equal to what, because as you can see, there's more area there. Okay, there is more area at the bottom than the area at the top, right? So if you perform your calculations, okay, so let me not conclude that because this height is different from this height. So the areas are different, right? The areas are different. So because of that, then you will have to inspect individually. So if we look at the right hand side, we can make use of it to find this y bar. When we find the y bar, this one is just geometry. Therefore, you can now find your qx. So if we want to find this side, then we will be able to just find the y bar, ya for the top area. The top area, if you look at the top area, it's not a regular shape. So you can take advantage of what we discussed last time. You can divide it into parts that are predictable. So if you look at this, you can try it this way. You can divide it into a rectangle and 2 triangles. Or you can divide it into, what else can you do here? Okay, this is not a, this is a what? Trapezium. Yeah, you can try that. Or you can actually do it this way and use 2 triangles, and also do it that way. You've got 2 triangles, right? So there are many ways, right? So there are many ways. So long and short of how you would go about it is maybe let's just try this one where we have these this rectangle and 2 triangles. Let's give these dimensions some names. Let's give these dimensions some names. So this is our 2x2, and then this is our height up to there. Maybe this is our A, side A. Let's just call it side A, from there to there. And obviously this would be the same by symmetry, side A. So we already have all the sides that we need. Geometrically, can you find these sides? Yep, I think you can find these sides. Why? Because you've got this height, you've got some side. As long as you have a height and a side, then you can use your geometry. So all these A and H and B, you can find a way to get them. Right, so since we are concerned with the equation, then we have to look at these 3 areas. So let's give them some names. I'll call this delta A11, delta A 12, and then delta A13. So what is the equation going to say? It will be 1 delta A11 plus y12 delta A12 plus y13 delta A13. Remember, we are just looking at area 1. So this would be y bar for area 1. Y bar for area 1. You will do the same for area 2, because in this summation we are looking at the 2 areas of the entire object. Right, so what is y11? Y11 is the centroidal position in the y-axis for area 11, and we can use this height. That will obviously be a third of the variable h, and you've got a value for that, so you can find it. Then your delta A11, is the area, so it's basically equal to your half times the base. Let's call that A times the height h. So you've got your area there. Y12 is the the y position for the rectangle, so it's obviously half of h. The area of a rectangle, it's obviously our 2x2 multiplied by the height h. Then what about the last one? The last one is obviously another 1/3 of h for this triangle 1, 3. 1/3 of h is the centroidal position in the y direction, and multiplied by the area. The area is obviously the same as the previous one, half of the base a times the height h. So there it means you can find your what? Your y1 a1. So which means your a1 would simply be, your y1 would simply be this whole sum divided by the area a1. If you're looking at your x, if you're looking at the bottom object, the method is the same. If you're looking at the bottom object, the method is the same. So this time you'll be constructing your y2, a2 being equal to y2, 1, a2, 1. So what is our a21? Maybe you can name it as that one. So that's your delta a21. The big one here will be your delta a22 and your delta a23. Right, can you find, let's say, C? Can you find C, the distance from here to there? Can you find it? Yes, you can. It's simply this 0.72 subtract this distance, right? How can you find this distance? You can use a what? You can use triangles, so there's several methods. You can actually use this height here, okay? So the geometry is something that you are used to, so I won't insult your intelligence. And then your y22. Remember, these y's for this second area are below the x-axis, so these would be negative. Don't forget that we are looking at position, right? Then your delta area 22, and then plus your y23 delta area 23, and you would find then your y2 bar by simply dividing all this by your a2. Perfect. So that is how you would use your equations for the first moment of areas. Now let's look at concept number 4 on composite plates and wires. You will notice that the geometrical shapes that we get and we need to figure out and work on are simply a number of regular shapes. There's simply a number of regular shapes put into what? Into one object. So figure 5.9, for example, it shows you that when we started and we were talking about finding the center of gravity, we looked at one individual body on which the sum of its weights was directed at what? At G. Now, if we are to divide this body into, instead of tiny particles, divide it into regular shapes. Why are we doing this? Because we now know that we can use regular shapes on the first moments concept to find their centroids. Remember as well that this method would apply here if the material is homogeneous. So by dividing this material into several shapes, we can find the the positions of the centers of gravity of the regular shapes. And by this method, we can then find the center of gravity. So if we are using centroids by the same method, one area can be divided into regular shapes. Instead of tiny particles now, we're looking at what? Regular shapes. Regular shapes, we will find some objects that have regular shapes. In engineering, there are quite a lot of objects that have regular shapes. So this is why this is important. So by dividing this regular shape now into what? Into areas A1, A2, and A3, you can then use your first moments concept to find the centroid. In this case, we will use the capital X for the centroid of the entire area, right? And then your small letters for the centroids of the sub regions that you've divided it into. So using the first moments equations, you can just as well find either the first moment or you can find the centroid of a regular shape. So look at your tables. So this is where you can now use your concept from the tables. Now, the concept of an area that is missing, which we saw in one of the slides earlier, where we had a rectangle with a void of a triangle. This can be used in this way. So the area where we have material would have some weight, obviously. The area where we have some material would have some weight. Then the area where we do not have some material would not have a weight. So we would actually assume that it had this material and this material was removed from it. So it's actually a negative weight. So when you are calculating the centroid of a regular shape, you can just subdivide the shape or the object into regular sub-shapes. Those sub-regions would have centroids that you can find in the table of centroids of two-dimensional bodies. Then you make use of that to simplify the centroid. So let's look at this shape. This shape has three sub-shapes. We have a semicircle. So that's a semicircle. Right, so let's just try and make this a little bit large, right? So we've got a semicircle. Then we also have a rectangle. Then we also have a rectangle. Then we also have a square, a circle. Then we have also a circle. So for these areas, if you want to find the centroid, you can now construct a table that that has a region or a piece of the material. So the first region is our region A1. What is the geometry? It's a semicircle. So if you want to find the geometry of a semicircle, you just jump onto your tables. The tables will show you some centroid calculation. Now, that centroid calculation, as you can see, our x-axis, this is where we have our y-axis. So this position is actually in the negative. For that reason, it will generate a negative first moment, right? Then its area is obviously positive just because we have material. The same applies for the second region, which is the rectangle. So it's a full rectangle, and its centroid is obviously half its length, and because it is conveniently located at the y-axis, then it's simply exactly half of its length. That is what gives us the x bar. Then the area is obvious, and then your first moment is actually positive. Now, remember, it's positive in the sense that if you look at the y-axis, you would see it rotate in the anti-clockwise direction. Now, the material that we are removing, which is the circular hole, the circular hole is positioned at a positive x-axis, so that's its centroid. How about its area? Its area is what? Is negative. Its area is negative. So we are actually removing, there is no material, so it's actually given as negative, so it gives us a negative first moment. So if you just add these up, then you can find your total x bar. If you add these up, you find your total area, and then if you add these up, you find your, in fact, if you multiply these, then you can just find your x bar A. These are the small x's, x bars. These are the small x's. Okay, so basically that is how you can decompose a composite body until you can find the first moments of individual regular shapes. So an example here is showing a triangular body. So knowing that the distance h has been selected to maximize the distance y bar from the line BB prime, right, which is the horizontal axis, to the centroid of the shaded area, show that y bar is equal to 2h over 3. So to show that y bar is equal to 2h over 3, we are looking for the first moment about the BB prime axis. So this would be Q about the B prime, which would be y bar, right? In fact, we are using the capital. So y bar times the area being equal to our summation of y bars, i.e. times the small areas, i.e. And we can see there that we have two areas. So I is equal to 1 up to 2, right? I is equal to 1 up to 2. So you can therefore tabulate. So you've got your region. Actually, let me write the equation there so that I can tabulate here. So you've got your region, and then you've got its what? You've got its y bar, and then you've got its area, and then you've got its first moment, y bar A. This column, the last one, is simply multiplying the first two. So this is now region 1, region 2, and then the total, which we can sum. Right, obviously the area of the total region is capital A, and then the areas is your half base times height. So let me just now divide this object conveniently. So I've got the large triangle, which we can call triangle, let's say PQR, right? And then the smaller one, PQR-STU, triangle STU. So this PQR forms our delta A1, this would be our delta A2. Okay, so by the same method, how can we find, so I will just use this side, and you can, it depends with how you want to write it, right? So this table is actually neat, but for you to see the math, I will do it on this side. So we want to find a y bar, so I will just write a y bar A being equal to, for the first triangle PQR, what is its y bar? What is its y bar? Remember, it's region number 1, triangle, the big triangle PQR. So for triangle PQR, our y bar is 1/3 of the variable A. 1/3 of the variable A. So 1/3 of A. Multiplied by its area is half of the base. The base is B, multiplied by the height A. So that would be half of AB. Perfect. So if we multiply the 2 here, we would have a 1/6 of A squared B. 1/6 A squared B. Just trying to be careful with the math there. I think it's right. So we now have the what? We have its centroidal position in the y-axis, which is 1/3 of its height, which is fine. We've got its area. Its area is half of the base times the height. And this is a positive material, right? In fact, there is material for the big triangle. So what we will do is to then subtract the second one. So for the second one, what is its y bar? It's obviously, again, 1/3 of, and we're still above the BB prime axis. So we will have a positive 1/3 of that. So that would be 1/3 H. Its area now is negative, isn't it? So its area is negative because there's no material. So we would write that area as half of, what is its base? Its base is KB, its height is H. So that would be minus, multiplied by minus half of BHK, isn't it? Half of BHK, KBH. Then that would form 1/6 of, the H is what will square, so KBH squared, half of KBH squared. So obviously, you would then need to add the two areas. So this is what you're doing here. It's just a summation of this and that. What are you doing here? You sum this and that to get this y bar. And then here you would sum that to get your y bar A. So which means that when you use your algebra here, it means you should come up with an expression shown up there. Right, so this one is a use of a large triangle subtracting a small triangle. Remember, the moment the equation is like this, it's now algebra. It's now algebra. You can even apply some calculus if you need, if that could actually give you some solutions. So that summarizes centers of gravity and centroids of areas. Centroids of areas are simply found using first moments. First moments are simply a moment of an area. Now we are looking at calculating centroids by integration, just because our bodies will not always be the perfect regular shapes. There are some cases where our body will look like that first object that we had. Looks like a what? It's a plate, but it's not a regular square or rectangle. So you can now use your calculus to find centroids. In this section, we'll cover just two concepts. So it's centroids by integration and areas and volumes of integration. Those are derived from theorems by Pappus-Guldinus. So these are two scientists or engineers that actually came up with these theorems. Okay, so you will learn how to make a cup. I think you've already done this though in your math, in your calculus. Right, so centroids by integration. How do we find a centroid by integration? We are just looking for a centroid. We know the definition of a centroid, and we know the equation of the what? Of the first moment. And we know the integral form of that equation. So the integral of the first moment, the equation of the first moment about the y-axis is x bar a, and it's an integral of x with respect to a. The same applies for qx, it's an integral of y with respect to a. Now the question is, what is that x? So this is now our what? Our x bar. Remember, those were centroidal positions. All those that were on the right hand side were centroidal positions, either in the y or in the x. So this is actually the centroidal position. So because it's a centroidal position and we are performing integration, we need to introduce something called an area element. This dA. We need to introduce something called an area element. If we were to summarize this method works in the following way. By definition, you have whatever first moment which you want to calculate, or the first moment that defines the centroid that you want to calculate. Now that you have it defined, you need to use what is called an integration strip or an area element. So you find the relevant equation and you pick an area element. This is what we will describe in this. The area element is what you will use to simply define your x bar element and your dA. When you have defined those, you will carry out normal mathematical integration. So it will just be the calculus later. So what are we trying to do? We're trying to figure out what is required. Then we choose an area element or a strip. Then when we've chosen an area element, we define its bounds, or its x element and dA, or its y element and dA. If you are given some area, you can choose three types of area elements which you want to integrate. You can choose a vertical strip as shown in the first figure. You can choose a horizontal strip as shown in the second figure, or a sectorial strip as shown in the third figure. So remember the objective. The objective is to define x element, define dA, or define y element and define dA in order for you to find either the centroid or the first moments. Right. So if we look at the geometry of the strip, this is now the geometry of the vertical strip, vertical area element. The vertical strip is in the material. So you've been given some area, so you create your vertical strip or your area element within the material. This vertical strip is very thin. How thin? It is as thin as a very small area element or a very small thickness element along the axis of concern. In this case, it's an x-axis. So that's our dx, the thickness of the area element. Then the height of the area element is basically our height from the axis up to some point P. So that's why our height is actually y. So therefore, if we want to find the centroidal x position of that, maybe we want to use it in this equation. The centroidal x position is simply this particular x coordinate. So that's the x position. That's why we have this x there. Then the centroidal y position is obviously half of its what? Half of its height. So if it's half of its height, then we have this y divided by 2 to get y element. So let's now get all the definitions. The definition of x element, we said x element is simply the x position of our strip. It is infinitesimally thin, so its thickness is its centroid is exactly at its point of thickness. It's very, very thin. So that's our x element. Then you can use it in that first moment equation if need be. Your y element, we've defined it. It's half the what? Half the height. Then dA is obviously length of the strip multiplied by the width of the strip. What is the length of the strip? The length of the strip is our height y. What is the width of the strip? The width of the strip is dx, which we defined here. This is why our dA is actually equal to y dx. Therefore, if you are to use, let's say you want to find qy. If you want to find qy, the equation is you are integrating x element dA. What you are just doing is, since you have defined all the parameters of your strip, you're just plugging in. So that will be an integral of what? X element is actually an x variable. dA is y dx. So it's multiplied by y dx. What is this y? Because x dx, we are happy, we can integrate that. But what is this y? As you can see, the y position, every y position is actually related to some x position. So you can actually find the function of that line. So your y is obviously the y at the top minus the y at the bottom. It's obviously subtracting a 0 every time. So whatever function, let's say this is y is equal to I don't know, x to the minus 2, whatever it is, that is what you will put there. So it's basically going to be, for example, integral of x multiplied by 1 over x squared dx. Everything is now in x, and then you look for your x initial, x final as your limits, x initial, x final, and you can integrate to find what? Qy. This means you can actually find your centroid x bar A using this method. The area, you already know how to find those. So basically, that is how you would use the vertical strip. All you need is to define the x element, the y element. Remember always that your y element is always half the what? The length of this or the height of the strip. Now, we're happy we have defined the elements for the what? For the vertical strip. So let me just make these things small, take them away maybe. Okay, let me just delete for the sake of space. Right, so let's look at the horizontal strip. Let's look at the horizontal strip. Horizontal strip or area element. The horizontal strip again is defined within the area of concern. So in this case, it is located either at this x final position, within the bounds of the x final position and this line, which we can say y as a function of what? Of x. So those are its limits. So what do we want to do? Once again, we want to define our x element, y element, dA as usual. So what is the x element? How can we find the x element? What did we say the x bar element is? It's the centroidal position of this what? Of this what? Horizontal strip. The area is obviously starting from this to that point, so obviously our centroidal position must be in the center. So by it being a position, we need to first find this position, which is what? Which is x. So if we were to construct this equation, we would write it this way. Our x element is actually equal to x bar element is equal to x, which is this position, plus half, isn't it? So it's plus half of, we would need what? X final minus, so good, we actually have an a. So it's like a minus x, half of a minus x. So here we have an x plus half of a minus half of x. And obviously your x minus half of an x will give you a positive half of an x plus half of an a. So this would obviously become half of x plus a. For this reason, we have this x element being defined simply by your position of this area plus the x value divided by 2. That's your centroidal x position. Your y, centroidal y position, the same way we're looking at the previous axis, all we need is distance from this position. So in actual fact, your y bar element is whatever y position it is at. Then your dA, we said dA is equal to the length times the width of the strip. So what is the length of this strip? It's obviously from here to there. So that would be, so let me put stars, right? So this is the length of the strip. So that would be our distance A from the origin minus, okay, we are looking at the strip, so it's minus x. So A from the origin minus x, that would be the length. Then its width is obviously dy. So that's why we have a minus x multiplied by dy. So that is how you would define your horizontal strip. Right, let me just take this away. The last one is a sectorial strip. So a sectorial strip would make use of the what? Of polar coordinates. So this is a sectorial strip. So that's your sectorial strip. I think now that you're used to it, you can tell that your x element is simply the what? The x position. So what we just need is this, which is actually a what? A centroidal position, because our x element is what? Is a centroidal position. So we know that if you take a sector and you approximate it to the limit where this angle d theta is very, very small, you actually have a right, you've got a triangle there. So this triangle actually has a base which is defined by delta S is equal to r d theta. Right, so for our x element is simply equal to this centroidal position. It's 1/3 from the base of the triangle, so it's 2/3 from our origin. That's why we have 2/3 of what? Of r cos theta. 2/3 of r cos theta. That's why we have that. The same applies. Your y bar is now just in the upward direction, so it's 2/3 of r sine theta this time. Our dA is just what? For us to find the area of a triangle, we would need half of the base times the height. So this is half of the base. The base, we said it's r d theta, so that would be r d theta multiplied by the height, which is an r. So in the end, you have half of r squared d theta, hence the definition of our dA. So it means that if you're now working out this, you can simply just get all your ducks in a row. First, define your x element, define your y bar element, define your dA, then you can perform the integration. So in this approximation, all we are doing is we are applying the same concept to lines. You can actually find the centroid of a line using this method. So that is why we have dl replacing our areas, right? And your definition of the dl that you would put there is also supplied there. So for your strips, all you're doing here is you're trying to find a centroid by integration, so that you can find you can use calculus. Write an example for the centroids of integration is supplied here. You want to determine the integration by direct integration, the centroid of the area shown. So express your answer in terms of A and H. Express your answer in terms of A and H. Right, so for this shape, obviously this is our origin. Let's annotate the shape. Okay, so remember, we want to find a strip. So let's choose a strip. So I'll choose a vertical strip, which is going to be looking like that. In that vertical strip, we know that its x element of this vertical strip is equal to the position x, right? So this is just an x position from the origin. What is its y element? Its y element is always half of the height for our vertical strip. So that would be our y bar element. Y bar element. So how do we get to half? We obviously, this is a position, so we need to start from here. So let's name these functions then. That will be y1, and this function will be named y2. So you've got your two functions, y1 and y2. Let's now use y1 and y2 to figure out the half position through the height of this strip. So our y element, y bar element, is equal to, obviously we start from y2, right? So that is this particular position. y2 plus half of what? Plus half of what? Of this thickness. Half of this thickness, or this height. What is the height? It's y1 minus y2. y1 minus y2. We are happy to see that our y1 is an h, our y2 is the function. It's proportional, isn't it? It's proportional, so it's y2 is given by what? H over a, that is the gradient, multiplied by x. So in actual fact, you can now put your h's and a's, and then you get your y element. How about dA? dA is length times width. What is the length of this, or the height of this strip? The height of this strip is y1 minus, so we know it's y1 minus y2. So that's its height. y1 minus y2. What is its thickness? dx. What is its thickness? dx. So if we want to find the centroid, this means from here we can use the first moment's equation. So we know that our x bar, okay, this is now non-regular, right? So x bar a is equal to the integral of x bar element multiplied by dA. So we are now applying our integral into this. What is x element? X element is x according to the vertical strip. What is dA? dA is the function y1 minus y2 dx. Minus y2 dx. So what are the limits? The limits are from the origin with respect to x, isn't it? The origin up to a. So from the origin up to a, we have our x. What is y1? y1 is a constant. y1 is the function on top. It's a constant. Its value is h. What is y2? We figured out it's a line that is proportional. So we've got an h over a multiplied by x, then multiply that by dx. So we've constructed our integral, right? This is now left to you. This is now calculus, isn't it? So you can actually take it from there. It will mean that you will now just need to have your x bar. You want to find the centroid, isn't it? You want to find the centroid, which is actually equal to some x bar, y bar. So your x bar is now found, isn't it? Your x bar is now found. Then you've got your integral divided by the area. How would you find the area there? I think you can use both. You can use the calculus is on this part, isn't it? So you can, for this is just a triangle, guys. So you can just use half base times height. So you've got your area. So I would just call this, let's call this the integral. So that would be an integral divided by the area of the triangle. So area of a triangle. Let me just write it, maybe half of the base. I can choose any. Let me just call this base h times the height a. And you're done. How about the y? The same applies. Y bar area is equal to the integral of what? Of y element dA. What is y element? It's defined. It's integral of y2 plus half of y1 minus y2. I think you can actually simplify that. Half of y1 minus half of y2 multiplied by dA, y1 minus y2 dx. This is getting interesting. Okay, with respect to x. So it's still with respect to x. So which means our limits are still 0 up to a. And then this part can simplify because you've got a minus half y2. So you've got a half y1, and then plus a y2 minus half y2. So we can actually write it as half into y1 plus y2, isn't it? Half into y1 plus y2. Then you've got your y1 minus y2 dx. Then your half can go out of the integral. Y1 plus y2, y1 minus y2. I think they are already seeing some difference of 2 squares. So you can then apply a difference of 2 squares. You know your function for y1, you know your function for y2, and you integrate away. And you find your y bar by, so let me just summarize this, by defining this as the integral divided by, so let's call this integral 2, integral 1 divided by half base times height. Right, so that summarizes your integration methods to find the centroid. You just use the first moment equation. So now we are at the last stage on finding areas and volumes of integration using Pappus-Guldinus theorems. So the theorems that we've looked at are Varinon's theorem, which was just vector, what is it called? We expand the vector by the distributive property. Now we just have Pappus-Guldinus theorem. So we don't have many theorems here. We've got mostly principles, and some of them are geometric. Most of them are geometric, actually. Right, so Pappus-Guldinus theorems basically define how one would get an area or a volume of integration from some geometry. It can be a line, it can be an area. So one should notice that if we are to find some surface area, if we are to find or make a surface area, you remember when we used to play with paper and fold paper to make a cylinder, right? So you just need some surface area that you make you turn it into some tube, you turn it into some circle. So that circular method, even a cone, you would take a shape, it could look triangular, then you find a way of turning it until it makes a cone. Or you can even use just normal A4 paper, but the way you turn it is such that you turn most of it at one point and then you turn less of it so that you've got that cone, right? Tip, and then you've got that. So basically, if you want to make a cone surface, all you need is a line, and then you rotate it about an axis. So Pappus-Guldinus is actually what you were doing when you were playing around, maybe as kids sometime, maybe just making some shapes. So this is a line which when you rotate, so if you rotate the line about an axis, it will generate a cone, right? It will generate the surface. Remember, a line will generate a surface of a cone. The same applies if you would take a semicircle and you would rotate it about the axis, it will generate a spherical surface. How about a circle? If you take a circle and then you rotate it about some axis in a circular direction, obviously, you would generate the surface of a torus or a ring, surface of a ring. So from that concept, Pappus-Guldinus came up with a simple definition of the surface area. So the theorem states the following. So the area of the entire surface of revolution that is generated by some length element is simply equal to the line L multiplied by the distance traveled by the centroid C in one revolution. The line L multiplied by the distance traveled by that centroid. So this is the centroid C. Distance traveled is obviously what? A circumference, isn't it? So this is why our small area element of this integration process to find the total area is simply given by 2 pi for the one revolution, y times dl. So where is our y? When you're looking at the entire object, it's actually at the centroidal position, y bar. So to find an area, all you do is you multiply 2 pi by the centroidal y position times the length. So this length for dl, it would be that. This means, can you see this? Can you see this? Can you see this? Do you remember where we saw it? This part of the equation, it's actually what was derived for us in these calculations. So this is what we are looking at here. That's your dl. Right. In other words, what we're saying is if you take this L to this side, that's what is defined where? Here. That is what is here. The same happens when you are generating a volume. If you want to generate a volume, all you need is what? Is an area. So if you have an area that is a square, a triangle, and you rotate it about an axis, it will generate a cone. So that's now a full volume of a cone. The same applies if you've got a semicircular area and you rotate it by 2 pi, you would end up generating a sphere. And then if you have a torus, it will be a solid ring this time, it won't be a tube. So the theorem basically states that an area, an element of area dA rotated about the x-axis generates a circular ring. So that ring is of what? Of volume dV. So Pappus-Guldinus theorem says the volume of that entire body of revolution is actually equal to the area of the region A multiplied by the distance traveled by the centroid, which is like 2 pi. So our dV is equal to our 2 pi y dA in the same format as the previous equation. And for us to find our volume, all we need is to multiply 2 pi. Can you see this? This is our Qx. So in other words, the volume of an object is simply 2 pi multiplied by its what? By its first moment. So here you can now apply Pappus-Guldinus in this example. So this example says determine the volume of the solid generated by rotating the parabolic area shown about the y, about the x-axis, and then about the right, excuse me. Is there something that is making some sound? Okay, I'm sorry if this timer has been making some sound and disturbing. I hope that it wasn't that bad. I'm sorry. I saw it make a sound for quite some time. Now I see that the sound might have been routing to the video. I just hope that it won't mess up everything. Right, so this last example is basically determining the volume of the solid generated by rotating the parabolic area shown about the x-axis and then the A prime. So if you want a volume by Pappus-Guldinus, we already saw that all we need is 2 pi multiplied by 2 pi multiplied by, if it's about the x-axis, right? If it's about the x-axis, we need a y bar, isn't it? Y bar A. So what is y bar? You already have the definition of the centroidal position for this kind of a shape. So the centroidal position in the y, I think it's already given as a function, so that would be 2 pi, and this centroidal position is a function of, in this case, a and h. So it's a function of a and h. And then you multiply it by the area. The area, again, it's a function of a and h. So basically that is what you would do there. How about the volume about the AA prime axis? The volume about the A prime axis would be 2 pi multiplied by the what? In this case, it's now the x centroidal position, right? Multiplied by the area. So that would be your 2 pi. Your x would be what? The centroidal position. This one is simple because it's just 2a, isn't it? This is symmetrical. So that would be your 2a, right? Multiplied by the area. The area is a function of a and h, as you will see in your tables. So basically that's how we would apply Pappus-Guldinus theorems. So for us to now have an idea of how this is actually practical, I want you to reverse engineer your mug, right? Your mug has got some volume. So find using Pappus-Guldinus the volume of your mug. and you can verify it by just pouring some non-volume. In fact, by pouring the total amount of water or whatever fluid you put it in, and then you put it into some measuring cylinder. So your mug is usually maybe something like this, right? So we can assume that it's cylindrical. So you can choose an axis, call that your y-axis. And all you want is to rotate this mug, or you want to rotate this particular region about the y-axis. So if you want to rotate this particular region about the y-axis, what you need is to define this function. You can actually approximate it to just be a square. So you can approximate it, make it a square, so that you can just rotate this rectangle about the vertical axis. When you do that, you generate the volume of your mug. So you need to measure your mug from inside and measure its diameter, so that this is just a radius of the mug. Use Pappus-Guldinus, so your volume will be equal to 2 pi multiplied by the centroidal position. So that will be centroidal position in this axis. And then you use that to then find so it can be x bar. It depends on what you choose. If you want it about the y, it will be your x bar multiplied by the area, and you're done. So reverse engineer to prove Pappus-Guldinus theorem. This covers the discussion on planar centers of gravity and centroids. My hope is that as you perform the calculations, you now have a better idea of what we are discussing here. Remember, with statics, it is very important that these principles be applied instead of read. You should read it, yes, for you to get the principle. You should revise it as we are maybe watching through the videos. But if you don't apply and work it out or carry out some tiny home experiment, then it is very difficult to remember. So I wish you the best in your chapter 5 on centers of gravity and first moments and volumes and areas of integration. It's goodbye. Thank you very much.